Hi, everybody. My name is Jacob White, and I'm a Jansky Fellow of the National Radio Astronomy Observatory. My talk is entitled "STARS or HaRd: How Unconstrained Stellar Emission is Interfering with Debris Disk Studies." So what I want to talk about today is what are debris disks, how do we observe them, and then go into some details about something called the MESIS project, which is specifically trying to understand how stellar emission can interfere with debris disk studies. So just to make sure we're all on the same page, I want to go over what are debris disks, since this is a term that could be a little bit foreign to some people. So debris disks are effectively the leftovers from the planet formation process. They're usually optically thin, ring-like structures, and all of the smaller dust and gas has been swept up into larger objects like asteroids, comets, planetesimals, or dwarf planets. Now, there can also be a lot of planet-disk interactions. So a planet in a system can influence both the size distribution of material along with the location and size of a particular debris disk. But there also, as the name kind of implies, a destructive process is ongoing. The disks are still dynamically active, which means that collisions of, for example, two asteroids could repopulate all of the small dust grains, which have been swept up into the larger objects. And these small dust grains carry most of the surface area in a disk. So that's actually what we observe when we observe a debris disk. To go into a little bit more on that, on how we actually observe them, there's three main ways. There's scattered light, which is where light is actually scattered off of the small micron-sized dust. There's thermal imaging, which is when you're observing the light coming from slightly larger grains. And by larger, I mean like millimeter to centimeter sized objects. And then there's inferred excess. This was actually the first technique used to observe debris disks. And how this works is if you have a star, which to first order approximation is a black body distribution, and then you have a continuous disk, that's like you take your tail of your black body, you make it a bit flatter. But then if you just have like a belt of debris material, it's essentially like you have two black bodies superimposed on top of each other. And if you know like what the emission from the star should be, and you see something larger than that, that's excess emission. And then you can use that to infer debris disk properties. So we'll talk about a couple of interesting systems and a similar underlying problem that they have. So the first is Proxima Centauri. This is our nearest neighbor. It has multiple disks and multiple planets. But does it have multiple disks? So ALMA observed 3 different debris disks around it, which was a really cool find. But upon further inspection, 2 of the debris disks, which were inferred through excess emission, turned out to be very, very large flares. And this should have been somewhat expected, given that M dwarfs are notorious for their flaring. But we can't really say anything about what excess emission could be there because these flares sort of like biased our observations. So another system I want to talk about is PHOENIX. This is one of the most well-studied debris disks, and it has multiple components. It might have some planets, and it's really nearby, so we have some really cool observations of it. But interior to the outer debris ring, which is very well resolved, is potentially another inner asteroid belt, which has been inferred through excess emission at infrared wavelengths. So we followed up on this with ALMA, and we, instead of finding an excess emission, we found a negative excess emission, which would sort of be like something that you wouldn't think is possible. But if we don't know what the base level of stellar emission is, then we're not going to know how much excess there could be. So it turns out we just don't know what's going on with these stars. In both of these situations, there's a problem in doing our debris disk science, and it lies with the stars. So to sort of address this problem, I came up with the MESIS project. This stands for Measuring the Emission of Stellar Atmospheres at Submillimeter to Centimeter Wavelengths. And this is an observational campaign with the goal of building a catalog of radio spectra of main sequence stars. So let's talk about this a little bit more. So typically when you think of a stellar spectra, you think of this sort of a plot, expands orders of magnitude, and it's really hard to compare different types of stars. So let's think about something a little bit different. And this is a brightness temperature spectra. So if we take the observed brightness temperature of a star and then normalize it with the photosphere temperature, we can compare different stars at the same time. Now, if it's a simple black body, it would just be this type of line, which you're thinking, okay, that's not a good approximation. But unfortunately, in debris disk studies, a lot of people assume that this is what the star is doing. Sometimes they go a bit further and say that it's slightly cooler than that based off of infrared data, but then they still extrapolate it to longer wavelengths and say this is what it's doing. If we look at our example of PHOENIX, we see that these two things are not right. So let's turn to something else. The sun. We have lots of observations of the sun. Let's see how that looks. Okay, maybe it's a little bit better, but it's still not the same. But the sun's a G-type star, Fomalhaut's an A-type star. So let's look at an A-type star if we want to compare it to another A-type star. So we observed Sirius A with effectively every radio telescope that would give us time, and we used that data to build a stellar atmosphere model with PHOENIX, and we find that the millimeter emission of Fomalhaut is pretty much the same as for Sirius A, so there's no really any evidence there for an asteroid belt at these longer wavelengths. And what we can say for sure is that these other two models mission really are not good at all. But there are other types of stars out there other than A stars and G stars. So we have observations of Gamma Virginis and Gamma Leptis. We use that data to inform KINICH-PAKAL models of the atmosphere. And you can see that the brightness temperature increases a lot, and that's due to the chromosphere and coronal emission that's in those. We also looked at Altair, which is a rapidly rotating star. And if you want to know more about that, I want to direct you to Francisco Tapia Vasquez's talk, which the recording should be available now. But what we know for sure is these models of emission vary wildly depending on the spectral type. And this is really just not a good model of emission anymore. So just a quick summary, we talked about what are debris disks, the leftovers of the planet formation process. We observed them through either infrared excess, scattered light, or thermal imaging. Talked about a couple interesting systems with Proxima Centauri and Fomalhaut. And the MESIS project is an ongoing observational campaign that seeks to observe and model stars at submillimeter to centimeter wavelengths with the ultimate goal of building a radio catalog of stars that can be used to observe unresolved debris. Thank you.